Good morning, ladies and gentlemen. Bet you didn't think you'd hear that since I'm not in the room today. All right, first of all, these two laws are almost identical to each other. The law of conservation of matter and the law of conservation of energy. The only difference between them is one word: matter and energy. Now remember, matter is anything that has mass and takes up space. Okay? Matter is anything that has mass and takes up space. Energy is the ability to do work. That is what energy is. Okay? So when we have the law of conservation of matter or the law of conservation of energy, their definitions are basically the same. Matter cannot be created or destroyed. It can only be changed. Okay? So for example, we could take sodium metal, we could take chlorine gas, and we could put them together. And with a little bit of energy input, we can make salt. Okay? Chlorine gas is a poisonous yellow gas. Sodium metal is a metal that reacts with water by dancing around on the top and bursting into flames. However, when you combine them chemically and change them, they become salt. Okay? That is what we mean when we say matter cannot be created or destroyed. It can only be changed. Energy cannot be created or destroyed. It can only be changed. If I hold this box up in the air, it has something called potential energy, which means that if I release it, it can do what? Fall. That's kinetic energy while it's falling, because it is actually moving. Now, how much kinetic energy does it have? It can't have any more than the potential energy that it began with. Okay? But that's what we mean about energy being able to be changed, not destroyed. Same thing is true with matter. Okay? Number two, what that means is that mass before a chemical reaction has to be equal to the mass afterwards. So if we have a certain amount of things that are reacting, the mass afterwards cannot be any more or any less than it was at the beginning. You can't make any more. You can't lose any. Now, when we say you can't lose any, we have to be careful. Why? Sometimes in a reaction, a gas is created. Where will a gas end up from a reaction? Off into the air. Well, that gas takes with it mass. So sometimes at the end of a reaction, you'll be like, well, there's less stuff here than there was at the beginning, Mr. Brand. You were wrong about that law of conservation of mass. No, we weren't. We just couldn't collect everything that was given off. And if we can't do that, then yes, if some goes off into the air, it's going to change our numbers in the end. Energy before a chemical reaction has to be equal to energy afterwards. Energy before and after also have to be equal. Now, just like sometimes mass ends up in a place we don't want it, sometimes energy ends up in a place we don't want it. Your car, what makes your car go? Gasoline. It has chemical energy in it that it converts to mechanical energy to move your car down the road. However, you only get about 40% of the energy out of the gasoline. Why? The other percent, 60% or however much it is, goes to overcoming things like friction, to making the parts in your car move. Some is lost as heat. So it's not that these things are not there, it's just that sometimes we can't always just add them up real easily at the end. Okay? In physical science, you probably did a lab with the skate park where we looked at the potential and kinetic energy as a skater moved up and down a ramp. Same idea here. Okay? Conservation of matter applies to chemical changes. Conservation of energy applies to any kind of change. If you are going to change chemically or physically, there is a good chance that energy is involved in that change. And that's why we are talking about energy right now. Questions? All right. A few terms for you, ladies and gentlemen. Matter we have already defined, right? Yeah. Matter is anything with mass that takes up space, mass and volume. Okay? That is the definition of matter. Do you want me to put them all up there and then talk about them, or do you want me to do it one at a time?
One at a time.
Okay. Mass is the amount of matter a substance contains. The amount of matter a substance contains. This stopper contains a certain amount of matter that makes it the size it is, also makes it the mass that it is. Okay? Now, the amount of matter in this stopper never changes, ever. Well, unless you cut it in half. But otherwise, it is not going to change. Now, as Jera and as Levi are drinking their water, or whatever it is that is in their cup, is the amount of water in their cup changing? Yes. But is it going away? No. It's leaving the cup, going into their bodies. Some is leaving and probably evaporating off into the air. But again, all of that matter is still accounted for. Okay? So, what is energy? Oops, sorry. So mass does not change. Now, the hard part about that is people think of living things. Well, aren't we matter, Mr. Wren? Yes, we are matter. Well, doesn't our mass change? Yes, because you're a growing living being. You take in energy. You take in food. You convert that into matter in your body. Okay? That causes you to gain or lose weight depending on what's going on with you. Okay? Energy is the ability to do work. Now, this is the scientific definition of energy. Energy is the ability to do work. Does it mean you do work? No, it means you can do work. So, that is what energy is, the ability to do work. Now, the mass of this stopper never changes. What determines its weight?
Gravity.
Gravity. Weight is the pull of gravity on this object. Now, what is causing gravity on this object right now? Let's hold on to that for a second. Okay? Weight is the pull of gravity on this object. If I put this on a scale, I can find the weight of it. However, if I take this object to the moon and weigh it on the moon, its weight will be 1/6 of what it is here on Earth. So if you or I want to be on the best weight loss program in the world, ladies and gentlemen, let's go to the moon. You'll weigh 1/6 of what you weigh right now on the moon. You weigh 120 pounds here on Earth, you'll weigh 20 pounds on the moon. You weigh 180 pounds here on Earth, you'll weigh 30 pounds on the moon. Now, your mass will never change. The amount of matter making you up doesn't. But your weight does. Why? The moon doesn't have as much gravity as does the Earth. So what's pulling on this object right now? The Earth. Pulling this object toward the center of the Earth or toward the ground from where we're standing. Okay? So weight changes depending on the amount of gravity. Weight changes depending on the amount of gravity. Oops, sorry. Gravity is one of several forces of attraction. Can you name me another?
That's what I was thinking.
Magnetism. Magnetism. Anybody have a third?
Love.
What? Nah, that's a bunch of bull. That's made up by Hallmark. The other one? Force of attraction between opposite charges. Positive and negative. Friction is not really a force of attraction. Friction is caused by forces of attraction. In other words, when two objects are rolling or sliding over one another or moving, gravity causes friction. Okay? But friction is actually trying to overcome gravity. Okay? Force of attraction between the center of mass of two objects. Is this object matter? Is the marker matter? Does it have mass?
Mhm.
Then does it have gravity? It does. Am I matter?
Yeah.
Am I made of mass? Do I create gravity? So how come this marker doesn't fly around me?
Gravity is practically nothing compared to the Earth's.
Correct. The Earth has a much larger pull of gravity than my body does on that marker. Okay? Now, I will give you a little hint here, gentlemen. If you want that special someone, and ladies, if you want that special someone to be attracted to you, take them out into outer space and be the most massive object around, and they will be attracted to you.
I don't think they're going to be attracted.
Well,
They
it'll
will
take-
be.
it'll
If
take-
you are the most massive object around, they will be attracted to you.
it'll take a
So
while.
whatever you do, if you're going into space, don't take Mr. Nast with you.
I mean, how are they going to be attracted to you when you die in like the first 3 seconds?
Who said they were going to die in the first 3 seconds? Give them a
Lord.
spacesuit.
Oh,
You don't have to make them. Gosh. Right?
You just said take them to space.
So again, whatever the most massive object is in space, other objects are going to orbit around it. Okay? Nadia, what are you laughing about? Nothing? You're the one who's going to rat me out. I'll bet on it.
Are you saying
I'll bet on it. Because I guarantee you I do this every year. I jokingly make fun of Mr. Nast. And by the end of the day, I'm getting a phone call from Mr. Nast. You're saying I got too much gravity again? Okay? If I'm the most massive object out, you're going to be attracted to me. That is just what gravity is, ladies and gentlemen. Now, you and I, unfortunately, probably will never, ever get to experience being in outer space. So what is always going to be the most massive object around that we are attracted to? The Earth. The Earth. Just the way it is. Okay? Just the way it is. But actually, ladies and gentlemen, is this clip attracted to the metal casing?
Yeah.
What force?
Magnet.
Magnetism. Is it still attracted?
Oh, not yet. Strongly.
Is it still attracted? That's my only question.
Yes. Yeah.
Cynthia, you're shaking your head no. So you think the magnetism is now shut off?
Yeah.
It's shut off. This knows that I'm no longer close to this and my magnetism shuts off. No. You're right. It is not attracted to it. Why?
It's not close.
Right. So what is it attracted to?
The Earth.
The Earth. Why? Strongest force always wins. It is still attracted to this metal. And if that were the strongest force, when I release this, it would go flying to here. However, it's not the strongest force. The strongest force is gravity acting on it. So again, now the strongest force is magnetism, stronger than gravity, which keeps it from falling to the ground. Okay? Strongest force always wins. Okay? Love is not a force, sorry. Because you know what a force is?
Romeo and Juliet.
I don't care. Force is a push or a pull. That's what a force is. That is the entire definition of a force. It either pushes things together or pulls them apart.
That sounds like love.
What?
That sounds like love. Yeah.
Oh my God. Get over it already.
I think Zendaya and Tom Holland.
I know love sounds like a force.
Young, naive, and not married, obviously,
You're a married
any of you.
man.
What?
You're a married man. You should
I
be
am.
strong of an attraction. Love is marriage is a job.
We'll move on.
Wow. Wow.
No answer.
Okay. Questions. Okay. All right. There are two kinds of energy that we're going to concentrate on first. They are the two most basic kinds of energy. One is called potential, one is called kinetic. Okay? Can anybody tell me what the difference between them is? Before we actually, is it on your slide already? Okay.
Isn't
No.
potential the ability to do work and kinetic is work?
Kind of. Kind of. You're so very close. To have kinetic energy, an object needs to be what? Moving. Kinetic means moving. An object has to be moving. Potential energy is stored energy. Energy that is waiting to be used. Okay? So when we talk about energy that is stored, it can be stored in three ways. By its position, by its deformation, or by bonds between the atoms. Okay? Is the ball moving?
No.
So what kind of energy does it have?
Potential.
Why?
Because of
Because
position.
it's stored.
Okay. And if I release it, it's going to do what? Fall. What causes it to fall?
Gravity.
Gravity, which creates kinetic energy because it then is moving. Okay? Why does the ball bounce back up when it hits the ground?
Wait,
Has a lot of energy.
because isn't there energy that's stored in the ball when it hits the ground?
Technically no. Well, yeah, kind of. How does it store it?
Newton's law.
First of all, when I hold it up, that's energy of what? Position, deformation, or bonds?
Position.
Position. Because it's above the ground, it can fall, right? When it hits the ground, though, what actually happens to the ball, which we can't see because it happens so very fast, is the ball compresses. That's deformation. Okay? That is now stored up energy. And then when it goes back to its original shape, it releases that energy and the ball bounces back up. Another great example of that, bow and arrow. You pull back on a bow, you have put potential energy into it. You can release it, boom, it'll send the arrow flying. Stretching a spring is deformation, or compressing a spring, either way, is deformation. You're storing up energy in there. And then the other way you could store energy is in the bonds of something. Strike a match. You're releasing energy as it burns. That was energy that is stored within the bonds of something. Okay? Now, we're not going to worry much about deformation and bonds. We'll talk about it, but we're not going to worry about it as much as we are energy of position. So look around the room and give me something that has potential energy. What? Which one? Why? Because it's up high. It could fall. What else?
Well, I mean, you could name any of the posters.
Any of the posters in this room. Because they are high, hanging on the wall, they can fall. What else?
Well,
Us?
technically,
How?
I know we're on the floor, but like.
Again, yeah, and again, I have people who say, well, Mr. Brandon, we're on the second floor of the building. What would happen if the floor opened up and we all fell down? Okay, you got me on that one. Okay, I'll go with that. Okay, point of reference is important when we're talking about position, though. Most things are not going to fall through the floor of this room, correct? Anything, though, that is above the floor level in this room is considered to have potential energy. Us, it's kind of tricky because if you're standing on the floor, technically you don't. But again, if you're saying you could fall out of your chair, okay, I'll let that go. Okay? What does potential energy depend on? It depends on mass and height of the object. It depends on the mass and the height of the object. How high the object is above the ground, how heavy the object is, determines how much potential energy you have. Now, I will never make you calculate potential energy, but I'm going to give you a formula anyway. And it is potential energy is equal to mass times gravity times height. Now, while I will not make you know what this formula is, I will ask you what are the factors that can affect your potential energy. Now, which one of these will we never see, or we will never experience changing? Gravity. Unless we're lucky enough to go off into space. I was getting to this earlier, and it just reminded me of what I was going to say. Far away from the door, is this still attracted to it? We've determined that, correct?
Mm-hmm.
But now at a further distance, that force is not strong enough to attract it anymore. But it's still attracted, correct? Here's another good weight loss program for you, ladies and gentlemen. Get on a plane and fly.
Stay on it.
Why?
You're further away from Earth.
You're further away from Earth, which is what you are attracted to. So technically, when you're flying in a plane, you will weigh less than when you're on the ground.
Is that why pilots are always so skinny?
No. It has nothing to do with that. And here's the thing. As soon as you're done flying and you come back to the ground, boom, weight's going to be the same. But the further you would get away from Earth, the less gravity you would feel. Just like the further I get away from the door, the less attraction this feels to it. Technically, you climb a high mountain, you'll weigh less on the top of a high mountain than you will down at Earth, at sea level. Okay? Now, you may not be able to notice it, you may not be able to detect it, but technically that's what happens. Units are joules. Joules are the units. Okay? Joules are the units. Now, energy is energy. I don't care what kind of energy. Energy is energy, which means everything that is energy could be measured in joules. Now, we don't with some things. For example, when you eat, what do we measure the energy in food in? Calories. You could convert from calories to joules, though. It's not a hard conversion. 4.184. Okay? Kinetic energy is energy of an object that is moving. Has to be in motion. Has to be moving. Okay? If it is moving, you have kinetic energy. If it is not moving, you don't. So what variables affect kinetic energy? Why would an object have more kinetic energy?
Speed.
No.
I don't know.
What?
Speed.
If it's moving, speed has got to affect it. What else?
Weight.
The mass. The mass. We use the term velocity because velocity is speed and direction. Understand it's basically the same thing, almost. Okay? Got a formula for you for kinetic energy. 1/2 mv squared. M being the mass, v being the velocity, and you square the velocity. What's the unit? Joules. Joules. I know you thought I ran away and left you. I didn't. Okay. So let's get into this, ladies and gentlemen. This is where we're getting into it. And the reason that we spent a bunch of time talking about kinetic and potential energy is because now we're going to relate it to something called KMT. KMT is kinetic molecular theory. What is a theory?
Educated.
No, it's a little bit more than that.
There was a definition for it,
The evidence supports it, but could be further.
but it could be changed.
Okay. A theory is something that the evidence supports. Absolutely correct. And it has been tested. And we get the same thing over and over again. But we're not 100% sure to where we can call it a law. Okay?
More evidence.
Gravity is a law. In other words, if I take an object and I drop it, I can measure how fast it is going to fall. And it doesn't matter what the object is. All objects fall at exactly the same speed. That's a law of gravity. Okay? You cannot deny that. It can be mathematically proven. Theories are the best explanation for all of the evidence we had. Now, an educated guess is just a hypothesis. Here's what I think is going to happen. A theory, we tested this and tested this and tested this, and this is the best we can do. However, maybe it's not 100% right. Now, there are 2 points to kinetic molecular theory, ladies and gentlemen, or KMT. And it is how we look at matter in chemistry. Point number 1, all matter is made up of tiny particles. Now, this part is indisputable. All matter is made up of tiny particles. What do we call them? Or molecules. There's a list of them right there, ladies and gentlemen. There are all of the different atoms known to man, including the ones that we have created. So on that periodic table up here, ladies and gentlemen, the first 92 elements are naturally occurring on Earth. The first 92 elements up to uranium are naturally occurring on Earth. From 93 to 118, we have created those in a laboratory somewhere. Okay.
Wow.
All right.
Wow.
Good. Okay? And those things make up everything around us. Those 92 things make up all the different things that you see around this room. So let me ask you this. Are there more atoms or are there more compounds? Compounds. Definitely. Otherwise, we'd be under, say, 236 different things. If it were just atoms and not compounds. Compounds are combinations of those things. Literally billions upon billions of compounds in the world. Okay? Those are the tiny particles that make things up. Your desk is actually made up of tiny particles. Your computer, your coffee cup, the plastic bag, your ID, everything around you, including you and I, is made up of tiny particles. Okay? That part is not the theory part. Now, what those particles are, that could be a theory. Now, we know there's atoms, we know there's compounds, but there's things that are smaller than the atom, which are what? What are they?
Protons, neutrons, electrons.
And there's actually evidence that there's still smaller particles than those out there.
Yeah.
That's the theory. Quarks. What?
Quarks, photons.
Well, actually, photons are bundles of light energy. They're not matter. Okay?
Yes, strings.
Yeah, strings, like on a guitar. Yes, absolutely.
Yeah.
Okay, point number 2, and this is the part that's the theory. Those tiny particles are in constant motion. Those tiny particles are always moving, which means they always have what? What? Kinetic energy. They always have kinetic energy. Now, here's the theory part. What would happen if we stopped them from moving?
They die.
We don't know. We've never gotten matter that cold that we have stopped the particles from moving.
Isn't that absolute zero?
That is absolute zero, yes. Okay? Never gotten matter that cold. We don't know exactly what happens. But we do know some weird things happen when we get close to absolute zero, when we cool things down. Okay? So that's the theory part of this still. Okay? But this is what chemistry is all about. These tiny particles that make things up. They are always moving. So right now, the particles in your desk are moving. Can we see them? No. Why?
They're so small.
They're so small. Okay? They're so small. Okay? I remember one time a teacher told me a story. They gave us these new hover cams, and the teacher was zooming in on their desk. And you know how sometimes pictures will get like pixelated? You know what I mean by that? Where it'll just have the little dots and things? And some kid goes, wow, are we looking at the atoms that make up your desk? No! You think these things have that good a zoom on them that you're going to look at the particles in your desk? Heck no. Okay? But It was a pretty good example because the pixels kind of moved around. Okay, they were tiny little particles. At least the kid had some science knowledge. Okay, so
Whoa.
now in terms of this, in terms of kinetic energy, means matter always has kinetic energy. Always. Okay, so this explains interactions between matter and energy. What's the temperature like today compared to the temperature like on Christmas? Colder. Now, out in front of East High School, we have a flagpole.
Yeah.
What state of matter is it? Solid. Made up of particles. According to this, those particles are always, how are they moving today compared to the way they were on Christmas Day?
Lower.
Why?
Because it's colder.
Okay. So when it gets colder, the particles have less what? Less kinetic energy. Now, what can change about the particles in the flagpole that affects kinetic energy? What are the two things that affect kinetic energy?
Velocity and mass.
Velocity and mass. Let me rephrase that question. What about that flagpole particles cannot change that affects kinetic energy?
Oh, no, the gravity. There's no gravity's potential.
Gravity has nothing to do with it.
This is such a good thing.
Come on. Okay, this tabletop. Made up of particles.
Yeah.
They're moving.
Yeah.
They have kinetic energy. What can't I change about those particles? I can't change the mass.
Oh, yeah, no.
Once we know what the particles are, we cannot change the mass, right?
Yeah.
Okay, you can't make these particles heavier. You can't make them lighter. So what is the only way to change the kinetic energy of this table?
Velocity.
To make the particles move faster or slower. How do I get them to move slower?
Cooling.
Okay, we come here tomorrow, the heat's out in the building, it's 20 degrees colder, these particles are going to be moving slower. We come in, the heat goes crazy, it's 10 degrees warmer, they're going to be moving faster. The particle size cannot change, but its kinetic energy still can. Why? Because you could change how fast the particles are moving. Okay? You could change how fast the particles are moving. Now that's different than what we said a minute ago. Compare the particles in this table to the particles in the air. They're at the same temperature. But what's different about the particles in this table compared to the particles of oxygen and nitrogen in the air? Their mass is going to be different. Which one's going to be heavier probably? Particles in this table or the particles in oxygen? Table. So that means these particles are moving how compared to the particles of oxygen in the room?
Slower.
Slower. Heavier object has to be moving slower to have the same kinetic energy as a light object. Okay? Something has to be the same though. The kinetic energy has to be the same. The mass has to be the same, or the velocity has to be the same for us to make these comparisons. Okay? Something has to be the same. All right. So, real quickly, ladies and gentlemen, you have all seen this already. Okay? Solids have a definite shape and a definite volume. What that means, ladies and gentlemen, is this book is not going to change its shape just because I put it in the cabinet, just because I put it on the counter, just because I put it on the floor. Now, what happens all the time is somebody says, well, Mr. Brandt, I could take and I could break that stapler. Then it doesn't have a definite shape. Yes, it still has a definite shape. You have just changed it. Okay? You have just changed it, but still has a definite shape. Yes. Hurry. Liquids have a definite shape, but no definite, a definite volume, but no definite shape. Means they take up a certain amount of space, but liquids will do what?
Fit their container.
They will take the shape of their container. They will deform, they will move, all of those things, but more importantly, they will take the shape of their container. Okay? Gases have no definite shape and no definite volume. They will take the shape of their container and they will do what? And they will fill their container. Gases completely fill their container, and this is a good thing because if we walk into the back of the room, we do not start choking to death because of lack of oxygen. Hope not. Okay? Gases take the shape of their container, they completely fill it. As far as the motion goes, solid, vibrational, and slow. Liquids Semi-free, they can move around but are limited. They can't get completely free of each other, and they have a medium speed. Gases are completely free. They spread out and they move as far away from each other as they can. So in terms of energy, solids have what kind of energy compared to gases? Less. They have low energy. Liquids are medium. Gases are high. Why?
Gases move faster.
Because gases move faster. The same particle as a solid, a liquid, and a gas has to have more energy as a gas because the particles are moving faster. Has to have less energy as a solid because they are moving slower. Questions? Okay, wonderful. Excellent. Phase changes real quick, ladies and gentlemen. Okay, what do we call going from a solid to a liquid? Melting. By the way, science also, chemistry also uses a special term, fusion. Okay? Fusion means melting. Okay? What do we call going from a liquid to a gas? Or boiling. Either one. The hard one going from a solid to a gas, skipping the liquid state. Sublimation. Sublimation. Why are these all in red?
They require heat.
Because they require the addition of heat. They require the addition of heat. The addition of heat, we use the term therm. Therm means heat. Endo means to put it in. Endo means inside. So you are going to be adding or putting heat into these things to get ice to melt and become liquid water. To get water to boil and become vaporous steam. Okay? Now, what do we call going from a liquid to a solid? Freezing. Actually, two other terms. Solidifying or crystallization. What do we call going from a gas to a liquid? Condensation. Where will you experience condensation?
Outside of your
On the outside of your drink on a warm summer day? Where will you experience it every morning, probably?
Walking inside.
Oh, not much dew out now.
or if you have a shower.
Could be, though, when you take a shower.
Yeah.
I don't.
You get out, the mirrors fog up in there, that's the condensation on there. Okay? Maybe you have a good exhaust fan, maybe that doesn't happen. So, a gas back to a solid is called deposition. Frost that appears on your car window, deposition. Water vapor in the air goes directly to a solid on your car. Why are these all blue?
They require less heat.
You're taking out heat.
You're taking away heat. You're taking away heat. Energy is being removed. Okay? Energy is being removed. Okay? We did what just now?
Take away heat.
No.
Turn it
Let's
off.
try this again.
Like,
Move that in.
Turn the lights on.
Oh, you're doing
What did I now do?
Turn off.
Took away the light. I didn't turn on the dark. You cannot turn on the dark, can you?
You done turned on the dark.
You can't turn on the dark. You cannot, ladies and gentlemen, add cold. You cannot add cold. What do actually? You take away heat. So if you're going to take a liquid and solidify it, you don't add cold, you take away heat. There is no way you can add cold. Okay? All right? All you can do is take away heat. Questions? Okay. So the last slide, I did it as a diagram. Here I gave you definitions for it. Okay? That's all I'm doing here is giving you definitions for it. Okay? So freezing and fusion or melting, process of going from a liquid to a solid or a solid to a liquid. By the way, these processes are what of each other? I want an easier term. Opposites, thank you. Stop, opposites, thank you. Inverse, you're trying to get a little too technical on me. I'm a simple person, let's go with opposites. Okay? These processes are what of each other? Opposites and opposites. Now, by the way, the definition or the difference between evaporation and vaporization. Evaporation is a process that happens all the time to water. It goes from a liquid to a gas only at the liquid surface. You do not have to heat it up. You do not have to add anything. It just naturally occurs. To get water to boil, you need to do what? Heat it up. Add energy. Okay? Add energy. So evaporation and boiling are slightly different, ladies and gentlemen. Slightly different. Questions? Please remember, some of the processes are exothermic, meaning you have to take and remove energy. Some are endothermic, meaning you have to put energy in. Questions? Let's see what's on the next slide. All right, this will be the last slide we get through today. Differences between evaporation and boiling. Evaporation changes from a liquid to a gas at the liquid surface. No energy is needed. Happens only at the surface. And only a few particles can do this. And I will give you time now to get caught up. So evaporation happens at the surface. Where does boiling happen? It does happen everywhere throughout a liquid. But where does it actually start?
At like the
base.
yeah.
Why the base? Why the bottom?
Or wherever the heat source is.
Yeah,
Thank you.
that's normally
Whatever is,
Think about
which you are correct. Normally, if you're on a hot plate on a stove, the bottom, which is why the bubbles start there and do what?
Go up.
Work their way up. So yes, it's a change from a liquid to a gas, not necessarily at the liquid surface, actually at closest to whatever the heat source is. Boiling, what do you have to add? You have to add energy. Energy has to be added.
to take away the cold.
You you take away the cold. You have less cold there. Okay? You go home at night and turn on the dark in your bedroom when you go to bed too. I understand. It happens closest to the heat source for boiling. Okay? And then you're right, once you get it up to a hotter temperature, it'll happen throughout the liquid. Evaporation only happens at the surface. And only a few particles can evaporate. Not all. What would happen if all particles evaporated?
Then we wouldn't have nothing.
We wouldn't have any liquid water on our planet. All right? We wouldn't have any liquid water on our planet. Okay? Boiling, any particle anywhere can do it because once you add enough heat to it, it will boil.
That's kind of scary.
What's that?
I think that anything could boil.
Well, let me rephrase that. Not every substance can boil, right?
Yeah.
Can you melt that iron pipe on the wall?
Yeah.
Could you boil it?
You could boil
I mean,
the
yeah.
liquid that
You can boil iron. You can take liquid iron and you can actually boil it.
That's weird.
Can you boil this wooden desk?
No.
Can you melt this wooden desk? What will happen instead?
Burn.
It will burn. So not everything can go through the states of matter. Some things, the bonds are too strong that instead of becoming a liquid or a gas, they will simply break apart and burn. You'll decompose it. Okay? Good. Questions, ladies and gentlemen?
All of us can do
All right, excellent, wonderful.
that. You wanna try that?
So now let's talk about what day is what color or whatever. No, we've had that discussion. We're done.
Monday is green. We agreed on that.
Why is Monday green? Because it's a go.